Hello everyone, in this video I'll show you how to solve the cutting wood problem. This problem is basically inspired by LeetCode cutting ribbons problem, which is a premium LeetCode problem, and I'll share the link to this problem in the description of this video. So it's a premium LeetCode problem, meaning that you would need a premium membership, LeetCode premium membership, to see the problem and to solve it in the LeetCode portal. So cutting wood is basically a similar problem. So let's first read the problem. Cutting wood, you're given an array of integers which are called wood lengths, where wood length of I represents the length of the ith piece of wood. You also have a target number k representing the number of equal length pieces you need to cut from these wood pieces. Your task is to find the maximum possible length of these k pieces you can cut. It's not possible to get k pieces. If it's not possible to get k pieces, simply return 0. And there are a couple of notes. You can cut a piece of wood into smaller pieces. Each piece must have the same length. You can't join smaller pieces together. The length of cut pieces can be an integer number. So, for instance, if you have a wood of length 4, you can cut this wood into smaller pieces, for instance, of length 2. So you can have two pieces of wood with length of 2, or you can also cut it to 4 pieces of length 1, or you can also cut into a piece of length 3 and 1, etc. So you can't go beyond 1. So it has to, the problem kind of deals with integers only. And yeah, so the main task is to find the maximal possible length for which you can have k pieces, so of that length. So let's see here is an example. If the wood lengths are 5, 7, 9 and k is 4, the output would be 4. That means that we can, from this set of 3 woods, we can have 4 pieces of length 4, but we can't have 4 pieces of length 5, 6, 7, etc. We can also have 4 pieces of length 3, 2, or 1, but since the task is to find the maximum possible length, so the output would be 4. And here is the explanation. From these 3 woods we can have 4 pieces of length 4. And how we can get them? So from wood of length 5, which is the first wood, we can cut 1 piece of length 4. From the second wood of length 7, we can also cut 1 piece of length 4. And from the third wood of length 9, we can get 2 pieces of length 4, because 2 times 4 is 8, which is less than 9. So the output is 4. There are also some constraints. I'm not gonna go through them. I'll just point out that the assumption is that the provided wood length integer array is never null, and it has at least one element in it. So arrays without elements, we can assume that they won't be provided in the input, and we don't need to deal with them. Additionally, as a second input parameter is the integer named k, which is the number of equally sized pieces that we need to create from the provided wood lengths. Before we move forward, just a quick disclaimer. In order to find an optimal solution for this problem, we will need to apply two known algorithm approaches. One is called greedy approach, and the other one is called binary search. Those are the known algorithm problem-solving approaches, and if you are not familiar with them, I would highly recommend getting yourself familiarized with these two approaches, because we are going to apply them to solve this problem. I would say that those two approaches are pretty standard and quite intuitive, quite not that difficult to understand. However, the binary search approach does have some important points, like around some edge cases. I slightly touch on that when I try to solve this problem. However, I can make a separate videos on these two approaches where we can discuss only greedy approach or only binary search approach and variations with these two approaches, so we can dive deep more into them. However, in this particular example, I'm not gonna be talking that much about these approaches. I'll just focus on solving the problem, and I assume that we are all familiar with them. So before we start, how can we solve this problem? So first of all, let's think about how can we solve. So first of all, we can think about some edge cases. So roughly, what can be the minimum possible value? What can be the minimum possible output in this example, and what could be the maximum possible output? So let's say if we have these three woods, so okay, obviously the minimum output is 0, but let's assume that there is a valid solution. 0 means that there is no valid solution. That means that this case probably very high, so we can't have that many pieces from the provided set of woods. However, in that case, the algorithm would return 0, meaning that there is no valid solution. However, if there is a valid solution, so what would be the minimum possible value? That can be the output here. The minimum possible value is obviously 1, because that means that we can create or k one-sized woods from the provided set of woods. So is 1 a possible solution for this problem here? It is. We can have 4 pieces of land 1, and we can get them all from the first wood. The first wood has the length of 5, meaning that we can have 5 pieces length of 1, and we need only 4, and it already satisfies the question that the requirement to have one size pieces. So 1 is a possible solution and is the minimum possible solution if there is a valid answer for any input for any set of provided woods and k. On the other hand, what would be the maximum possible value? The maximum possible value is obviously equal to the maximum value in this provided array. So in this particular case, it's it's 9. Okay. Why is 9? So in this particular case, can we have 4 pieces length of 9? We can't, because we can get 1 piece from the third wood, but we can't get them from the second or the first wood, meaning that in this particular case 9 is not the solution. However, generally speaking, 9 can be a solution. Imagine that this k is 1, so can we have one piece of length of with length of 9 from this provided set of length of woods? Yes, we can take the third one, and we have one piece of with length of 9, meaning that it's a valid solution here, and probably the final outcome for this particular input. Anyway, if k is 4, we can't have it, the solution can't be 9. So we define two potential minimum and maximum values for this particular problem, and we know that for any given input array and any given k, the minimum solution cannot be lower than 1 if there is a valid solution, and cannot be greater than the maximum value in the provided array, which is 9 in this particular case, because it cannot be 10, because we cannot get we cannot get a piece of land with length of 10 out of these 3 pieces here, because none of them has the total length of 9, and we cannot merge 2 pieces. We can just cut them, and that's why the maximum value in the provided array is the maximum possible output for any given input array. So let's make this statement a little bit more general. So for any given input array and k, the minimum value the minimum value can be 1, the maximum value is the max in wood lengths if there is a valid solution. So if there is a valid solution, it will be a number between 1 and the maximum value in the provided array. On the other hand, it will be 0 if there is no valid solution. So this is an important thing to notice. So we have identified the minimum and maximum possible values for any given input. So how are we going to approach and solve this problem? So one potential solution could be, we can simply start iterating this array of possible solutions and say, can we get a valid solution with the minimum value? And if the answer is yes, then we identify a potential solution. So we will switch to the next value, which is 2. Can the output be 2? Can it be a valid solution with a piece size 2? If the answer is yes, we can continue and find the next and try to do the same for the next value, which is 3, 4, 5. And once we reach the value for which we can't get a valid solution, or once we reach the maximum possible value. So the last value we identify as a valid solution will be the outcome of the problem. So we will start, can we get a valid solution for value 1? If the answer is yes, we will try for the with the value 2. If the answer is yes, we will try with the value 3. If the answer is yes, we will try with the value 4. If the answer is yes, we will try with the value no, with the value 5, and in this particular case, value 5 is not possible. So we can't have 4 pieces, each having length 5. So the answer is no. And for 5 is no, then it will be no for 6, for 7, for 8, and for 9. So we will get an array of yeses and nos, and we need to find the maximum possible value. So this is for 1, this is for 2, this is for 3, this is for 4, this is for 5, this is for 6, 7, 8, and 9. And the answer is the yes value for the greatest number here, which is 4. So we are one step closer to the solution. So instead of us doing this for values 1, 2, 3 linearly, so we can do something better. We can apply the binary search approach, and we can start with a medium value. For instance, it will be value 4 in this particular case, and say if the value is yes, if we can have a valid answer for a piece with length of 4, we can ignore the left half of this array and do the same approach only with the right half of the array, and split it to half and search for the medium value of this right half. And if it's no, we can go back to the left half of the remaining items, and so on until we find the optimal solution. So instead of us going linearly through this array, we can apply the binary search method and go basically in each iteration we can get rid of the half of the items. In the worst case scenario, we will iterate how many times. So this is from the binary search topic. So we can iterate logarithm of the length of this array. And what is the length? What would be the length of this array? Well, it will be the length of the maximum possible value in the provided array of woods. So it will be, let's call it max of wood lengths. And what would be the base for this logarithm? It would be 2, because that's how many times we iterate in the worst case when we are applying a binary search. So we will, instead of, if we were doing this linearly, one by one, in the worst case we would iterate through the whole array, and instead of logarithm max of wood lengths times, in the worst case we would be iterating max length time, which is a value which is a greater value, so which is basically more times. So it's less optimal. So we can ignore this linear approach and we can focus on the binary search approach. So to minimize the number of iterations through this array. And finally, there is one more missing piece in this problem. Let's say that we have a value 4, and for which we need to figure out whether there is an optimal, a valid solution or no. So basically, how can we answer for a given value 4 whether it's the answer yes or no? So what we can do, we can simply iterate through this provided array of woodlands, and we can apply the greedy approach. And the greedy approach means that we will take the first element and see how many pieces of land of 4 can be made of the first wood. It's 1, right? We can cut 1 piece of land 4. So we can memorize that somewhere. 1 from the first. From the second we can have also 1. So 1. And from the third we can have how many? 2 pieces of land of 4. So it's 2. And we can, when we sum up these 3 numbers, we are getting the number 4, which is a valid solution because this number is 4 is greater or equal than the number that we are trying to solve in this particular iteration of this binary search. So when we find a successful valid answer for this 4, the answer is yes, then we continue the search in the right size of this array, and we will probably take number 6, and for 6 we can do the same thing. How many times, how many pieces from the first wood we can cut? 0 pieces, because 5 is less than 6, so we cannot have a single piece from the first wood. From the second wood we can have 1, and from the third wood we can have also 1. So the total number is 2, which is less than 4, which is less than k, which means that for land of 6 we will say no, and we will then continue the iteration for the left half of the remaining items. So we will do the same for 5, and the answer will be no, and the last valid answer is for 4, and that's why the optimal solution in this case is 4, and the answer to this particular problem, or the output. So what would be the time complexity of this particular single check for a single number? Well, we need to go through in the worst case through the whole array of input of the wood lengths. So which means we need to linearly go through the whole array. So one check for one iteration of this binary search would take, in the worst case, the length of this array checks. So we can say that this greedy approach would take, a single greedy approach would take the length or the size of wood lengths. So what would be the time complexity for the whole problem? Well, it would be the number of binary search iterations times the complexity of this single check, greedy check. So the overall time complexity of the solution would be logarithm of maximum value of wood lengths for the base of 2 times len of wood lengths array. So this would be the time complexity. So now when we explain the approach we are going to take, let's try to implement this solution. So here we have a max length method, which takes 2 input parameters. One is the wood length, which is an array of integers. The second one is k, which is the number of equally sized pieces we need to cut from the provided woods. So let's start with this approach. The first thing we need to do is we need to calculate the maximum and minimum values. So maximum value would be int max. We can initially set it to be 0, and we can simply iterate through the provided wood length array and find the maximum value. For each integer wood in the wood length, we can say maximum is equal math.max. Max is a helper function from the math class. It's part of the standard Java. Yeah, I'm using Java language here, but it should be relatively straightforward to implement the same thing in any other language. So max function would take, or method would take 2 integers and return the maximum value between the 2 integers. So this local variable max will, at the end of this for loop, have the global maximum value from this provided array of wood lengths. So it would be max wood, and now we have the maximum value. Yeah, as you have probably noticed, I'm not checking whether the wood length array is null or is empty. Maybe we can add those 2 checks as well, but for the sake of simplicity we can ignore that. And also in the constraints it's listed that wood length can't be null nor has 0 elements, so we can ignore that check. And also in the total time complexity of the solution, we haven't taken into consideration this maximum value calculation, so we can add it. So it would be we will iterate again through the len of wood length times linearly through this array. So the solution would be len of wood length plus logarithm of maximum value times the size of the wood length array. Given that this is smaller for the big inputs than this part, then we can assume that the total time complexity of this solution will be driven by this second part of the formula, and actually is the total time complexity for the overall solution. So understanding the time complexity and how we calculate the time complexity of a solution is a third topic, which is again not part of this video, and we can have a third video discussing only how to measure a time complexity, the time complexity of a problem. So this is also something I would like you to read about or get yourself familiarized, because it really drives the the overall solution. When you try to find an optimal solution, that means that you need to find an optimal solution with the lowest possible time complexity, or maybe space complexity, which we haven't touched that in this video. But yeah, that's something you need to know in order to so you can figure out the best possible solution for a given problem. So yeah, let's continue with coding. So now we only have the maximum possible value. Now we need to figure out the left bound and the right bound of our binary search approach. So for the left bound, it would be the minimum possible valid value, which is 1. For the right bound, we can use the maximum value, and we can add an extra 1. Why extra 1? This is an edge case for the binary search, and this is something that I'll explain in the binary search video. Here we don't have time to go through it, but these edge cases are quite important, because if you end up setting the wrong left and right bound, your overall solution, or although the idea was good, would not work correctly. And this is something I would really encourage you to dive deep on and to try to understand these edge cases, especially if you're preparing for a coding interview, because during a coding interview for some big tech companies, you have a very limited amount of time, let's say 15 minutes per problem, and it's really not enough time for you to spend on understanding these edge cases. So highly recommend to get yourself familiarized with binary search and its edge cases in advance. So left and right are 1 and maximum value plus 1. And so let's implement the binary search. So while left is lower than right, let's calculate the medium value. Medium value would be left plus right minus left divided by 2. So this is going to be the medium value. So someone may ask, why this way? Why can't we simply say m is equal to left plus right divided by 2? It should be similar, right? Well, it would be similar, however, and it would be a great question. However, this option has a tiny problem, because these numbers, right and left, those are integers, and integers have a value range. So and if left and right values are close to the maximum possible value, so you can find the maximum possible value in Java, it should be, yeah, there is a max value constant, and if you check it, okay, it's in hexadecimal notation, but this value is the maximum possible value for an integer. So imagine that both left and right are close to this maximum value. This approach here, when we sum up left plus right, would breach that maximum possible value, right? And it would cause a problem or a bug in the solution, so it wouldn't work well. So you can either, and this all depends on these input constraints. So I think that we don't need to go that much into details. Our goal here is to understand the overall solution. So it's just a tiny note why I chose this formula, because here we never sum up right plus left. we subtract left from right and then add it to the left value. So this is a tiny optimization which would deal well with those edge cases when left and right are very big, huge numbers and closer to the maximum integer value. So yeah, medium value is somewhere in between left and right. And now what we need to do, we need to check whether there is a valid solution for this medium value. How we are going to do this? We are going to iterate through the input through the array of woodlands. So we will say for each wood in woodlands, and I'll create a temporary variable which is initially equal to 0, and I will I will add to this value for each wood how many pieces of land of M can be cut, and I will sum up all of these pieces for every single wood. So I will do something like wood divided by M, right? So for the first wood I can have this many pieces of land of M. Additionally, before this while statement, I'll create an integer result which is initially equal to 0, and that result will be returned at the end of this function or method as a final result. If we can't have any valid response, it will remain on this initial value, default value 0, and it will return 0, meaning that there is no valid solution. In any other case, we will update this result for any M that we find. So at the end of this iteration, this temp would be the maximum possible value of pieces of land M. So what we need to check whether this temp value is greater or equal than M, meaning that there is a valid solution for this value M. So if temp is greater or equal than M, then result, we will update this result variable, would be equal to M, and we need to continue the binary search in the right half of the array of possible solution. So we will say left is equal to medium value plus 1. Otherwise, if there is no valid solution for M, let's try with smaller m's. So we will update the right bound of the binary search. We will say right is equal to M. Again, these are some may ask why here M plus 1 and why not M minus 1 here. Again, those are these edge cases depending on what kind of problems we are trying to solve with binary search. So in this, we need to be extra careful here with these edge cases to avoid ending up in an infinity loop. That's why for this particular case I've chosen left to be strictly less than right, and I chosen this way of updating the left and right boundaries. However, if you want to dive deep more into why this way, yeah, I'll create a separate video on binary search approaches only, and we will discuss them. Okay, once left becomes smaller than right, we will end this binary search and we will return the result, and result will always be the greatest possible valid solution. Why? Because we only update. So if you go back to this yes and no array, if you find one yes, the next found yes will be for a greater value. We will eliminate all the smaller values, so there's no need for some extra checks for this result. It will simply always be the greatest possible value. And this should be the solution to our problem. Finally, let's just try to test this approach. By the way, I created a class called solution with this function or method named maxLine, and let's just create an instance of this class solution equals new solution, and let's say int wood length, new int, let's use the same values as here, 579, and k is 4. And let's print let's see what happens. The result is 4 as expected. However, this is just one of the potential inputs. So in order to verify this solution, we will need to test against various inputs, so which tests different use cases, different edge cases, etc. For this purpose, I already prepared a set of various inputs. So this is the base case. Also, there are some other interesting examples. For instance, minimum possible case when array has only one input array has only one element, size of 1, and k is 1, etc., etc. These use cases are really good to test the edge cases in your binary search, whether you configure the left and right boundaries correctly, whether your condition to exit the while loop in the binary search is well implemented, etc. So instead of me testing every single test case manually, I'm going to just create an instance of this solution test. The solution test already creates a solution and executes the maxLine function or against different inputs. So let's try that. Solution test, and let's say solution test run tests. When we execute this, oh, we have a problem, which is great, which is let's see which test failed. Test case number 2 failed. Let's see, test case number 2 for 3, 4, 5, and 7 is expected value is 1, but we got 3, 4, 5, and 7. We got 3, which is obviously not possible. So how are we going to test this? Let's go 3, 4, 5, and k is 7. 3, 4, 5, k is 7. Let's comment out this solution test, and let's add a breakpoint here, and let's debug this. Okay. Let's see what happens. So maximum value is 5, which is correct. Left is 1, right is 6, that's correct. Medium is 2. For 2, it's 3. For 3, we can have okay, temp here is 3. Why is it 3 for each wood? So wood is 3, 4, 5. 3 divided m is 2. 3 divided by 2 is 1. 4 divided by 2 is 2. Oh, okay, here is the problem. So we compare temp with m, but we need to compare temp with k, right? So whether this value is greater or equal than k, because we need k number of pieces, not m number of pieces. M is the size of the piece. So let's give it a try here again. So result is 1, and let's execute this solution test again, and now all tests have been passed. Okay, so this would be a solution to this problem. And finally, let's just think about some potential optimizations. Here, for instance, there's no need to iterate through the whole array of woods. We can simply end this for loop as soon as temp becomes equal or greater than k. So at the end of every single iteration in this for loop, we can simply check if the temp is already greater or equal than k. Then just we can simply break the loop, and if you execute this, yeah, this also works. And one more thing, this result here can probably be removed, and we can use the left or value for the final result. So I'm not going to make that change here. That would be a question for you. How would you eliminate this result variable, which is probably not needed, and we can completely rely on the left variable instead? So you need to slightly modify this code and implement and eliminate the result. So that's a question for you, and do let me know if you have any further questions. I hope you liked it, and that would be all for this video. Thank you.